I think we're all reasonably familiar with the three states of matter in our everyday world. They're at very high temperatures, you get a fourth. But the three ones that we normally deal with are things could be a solid, a liquid, I'll do that in blue, although it doesn't have to be blue, or it could be a gas. And we have this general notion, and I think water is the example that always comes to, at least to my mind, is that solid happens when things are colder, relatively colder. And then as you warm up, you go into a liquid state. And as you warm up even more, you go into a gaseous state. So you go from colder to hotter. And in the case of water, when you're a solid, when you're a solid, you're ice. When you're a liquid, some people would call ice water, but let's call it liquid water. Liquid water, I think we know what that is. Liquid water. And then when it's in the gas state, you are vapor or steam. Vapor or steam. So let's think a little bit about what at least in the case of water, and the analogy will extend to other types of molecules, but what is it about water that makes it solid and when it's colder, what allows it to be liquid? And I'll be frank, some liquids are kind of fascinating because you can never you can never nail them down, I guess is the best way to view them, or a gas. So let's just draw a water molecule. Water molecule. So you have oxygen there. You have some bonds to hydrogen, and then you have two extra pairs of valence electrons in the oxygen. And we did a couple of videos ago, we said, hey, oxygen is a lot more electronegative than the hydrogen, and that it likes to hog the electrons. So even though that this shows that they're sharing electrons here and here, right? At both sides of those lines, you can kind of view that hydrogen is contributing an electron and oxygen is contributing an electron on both sides of that line. But we know because of the electronegativity or the relative electronegativity of oxygen that it's hogging these electrons. And so the electrons spend a lot more time around the oxygen than they do around the hydrogen. And what that results is that on the oxygen side of the molecule, you end up with a partial negative charge. And we talked about that a little bit. And on the hydrogen sides of the molecules, you end up with a slightly positive charge. You end up with a slightly positive charge. Right there, slightly positive. Now, if you have very little, I guess the best thing is if these molecules have very little kinetic energy, they're not moving around a whole lot, then what the positive sides of the hydrogens are very attracted to the negative sides of oxygen in other molecules. So let me draw some more molecules. So when we talk about the whole state of the whole matter, we actually think about how the molecules are interacting with each other, not just how the atoms are interacting with each other within a molecule. So let's say that I just drew one oxygen. Let me copy and paste that. Control paste. But I could do multiple oxygens. And let's say that that hydrogen is going to want to be near this oxygen because this has partial negative charge. This has a partial positive charge. And then I could do another one right there. And then maybe we'll have, and just to kind of make the point clear, you have two hydrogens here. Maybe an oxygen wants to hang out there. I'll do it so maybe you have an oxygen that wants to be here because it's got its partial negative here, and it's connected to two hydrogens right there that have their partial positive. But you can kind of see a lattice structure being, and let me draw these bonds, these polar bonds that start forming between the particles. And these bonds, they're called polar bonds because the molecules themselves are polar. And you can see it forms this lattice structure. And if each of these molecules don't have a lot of kinetic energy, or if we say the average kinetic energy of this matter is fairly low, and what do we know is average kinetic energy? Well, that's temperature. Then this lattice structure will be solid. These molecules will not move relative to each other. They're all, I could draw a gazillion more, but I think you get the point that we're forming this kind of this fixed structure. And while we're in the solid state, as we add kinetic energy, as we add heat, what it does to the molecules is it just makes them vibrate around a little bit. So the kinetic energy just makes these, if I was a cartoonist, the way you'd draw like a vibration is put little quotation marks there. That's not very scientific. But they would vibrate around. They would buzz around a little bit. I'm drawing arrows to show that they're vibrating. It doesn't have to be just left, right. It could be up, down. But as you add more and more heat in a solid, these molecules are going to keep their structure. So they're not going to move around relative to each other, but they will convert that heat, and heat is just a form of energy, into kinetic energy, which is expressed in these as the vibration of these molecules. Now, if you make these molecules start to vibrate enough, and if you put enough kinetic energy into these molecules, what do you think is going to happen? Well, this guy is vibrating pretty hard, and he's vibrating harder and harder as you add more and more heat. This guy is doing the same thing. At some point, these polar bonds that they have to each other are going to start not being strong enough to contain the vibrations, right? And once that happens, the molecules, let me draw a couple of more. Once that happens, the molecules are going to start moving past each other, right? They'll start moving past each other. So now all of a sudden, the molecule will start shifting. The molecule will start shifting. But they're still attracted to, maybe this side is moving here, that's moving there, you have other molecules moving around that way, but they're still attracted to each other, right? Even though we've gotten to the kinetic energy to the point that the vibrations can kind of break the bonds, can break the bonds between the polar sides of the molecules, it's still our vibration or our kinetic energy for each molecule still isn't strong enough to completely separate them. They're starting to slide past each other. And this is essentially what happens when you're in a liquid state, is that you have a lot of atoms that are they want to be touching each other, but they're sliding. They have enough kinetic energy to slide past each other and break that solid lattice structure here. And then if you add even more kinetic energy, even more heat to the at this point it's a solution now, you're going to break. They're not even going to be able to stay together. They're not even going to be able to stay near each other. If you add enough kinetic energy, they're going to start looking like this. They're going to completely separate and then kind of bounce around independently. Especially independently if they're an ideal gas, but in general, a gas is they're no longer touching each other. Maybe they might bump into each other, but they have so much kinetic energy on their own that they're all doing their own thing and they're not touching. And I think that makes kind of intuitive sense if you just think about what a gas, for example, it's hard to see a gas. Why is it hard to see a gas? Because the molecules are much further apart. So they're not acting on the light in the way that a liquid or a solid would. And if we keep making that extension further, a solid, well, I probably shouldn't use the example with ice, because ice or water is one of the few situations where the solid is less dense than the liquid. That's why ice floats, and that's why icebergs don't just all fall to the bottom of the ocean, and ponds don't completely freeze solid. But you can imagine that because a liquid is, in most cases other than water, less dense, that's another reason why you can see through it a little bit better, or it's not diffracting. Well, I won't go into that too much, than maybe even a solid. But the gas is the most obvious, and it is true with water. The liquid form is definitely more dense than the gas form, that the gas form will kind of, the molecules are just going to jump around, not touch each other, and because of that, more light can kind of get through the substance. Now, the question is, how do we measure the amount of heat that it takes? The amount of heat that it takes to do this to water. And to explain that, I'll actually draw a phase change diagram, which is a fancy way of describing something fairly straightforward. So let me say that this is the amount of heat I'm adding, and this is the temperature, and then we'll talk about the states of matter in a second. So heat is often denoted by Q. Sometimes people will talk change in heat. They'll use H, lowercase, uppercase H. They'll put a delta in front of the H. Delta just means change in. And sometimes you'll hear the word enthalpy. And let me write that because it was a word that I used to, I'd say, what is enthalpy? It sounds like they're using it, enthalpy. It sounds like empathy, but it's quite a different concept, at least as far as my neural connections can make it. But enthalpy is it is closely related to heat. It's heat content. It's heat content. Heat content. For our purposes, when you hear someone say change in enthalpy, you should really just be thinking of change in heat. I think this word was really just introduced to confuse chemistry students and introduce a non-intuitive word into their vocabulary. The best way to think about it is heat content. Change in enthalpy is really just change in heat. And just remember, all of these things, whether we're talking about heat, kinetic energy, potential energy, enthalpy, you'll hear them in different contexts, and you're like, oh, I thought I should be using heat, and they're talking about enthalpy, or these are all forms of energy, and these are all measured in joules. And they might be measured in other ways, but the traditional way is joules. And energy is the ability to do work. And what's the unit for work? Well, it's joules, force times distance. But anyway, that's a side note. But it's good to know this word enthalpy, especially in a chemistry context, because it's used all the time, and it can be very confusing and non-intuitive. Because you're like, where did this enthalpy? I don't know what enthalpy is in my everyday life. Let's just think of it as heat content, because that's really what it is. But anyway, on this axis, I have temperature, or no, I have heat. Right? So this is when I have very little heat and I'm increasing my heat. And this, say, is temperature. Temperature. Now, let's say at low temperatures, I'm here. And as I add heat, my temperature will go up. Right? Temperature is average kinetic energy. Let's say I'm in the solid state here. And I'll do the solid state in purple. And so as I add heat, no, I already was using purple. I'll use magenta. So as I add heat, my temperature will go up. Right? Heat is a form of energy, and when I add it to these molecules, as I did in this example, what did it do? It made them vibrate more, or it made them have higher kinetic energy, or higher average kinetic energy. And that's what temperature is a measure of, average kinetic energy. So as I add heat in the solid phase, my average kinetic energy will go up. And let me write this down. This is in the solid phase. Solid, or the solid state of matter. Now something very interesting happens. And let's say this is water. Let's say this is water. So what happens at this is 0 degrees. I'll do 0 degrees, or which is also 273.15 Kelvin, 0 degrees Celsius. But let's say that's that line. What happens to a solid? Well, it turns into a liquid. Ice melts. And not all solids. We're talking in particular about water, about H2O. So this is ice in our example. All solids aren't ice, although you could think of a rock as solid magma, because that's what it is, right? You can think of I could take that analogy to a bunch of different ways. But an interesting thing that happens is at 100 degrees or at 0 degrees, right? Depending on what direction you're going, either the freezing point of water or the melting point of ice, something interesting happens. As I add more heat, the temperature does not go up. As I add more heat, the temperature does not go up for a little period. Let me draw that. For a little period, the temperature stays constant. So, and then while the temperature is constant, it stays a solid. We're still a solid. And then we finally turn into a liquid. Let's say right there. So we added a certain amount of heat and just stayed a solid, but it got us to the point that the ice turned into a liquid. It was kind of melting the entire time. That's the best way to think about it. And then, once we keep adding more and more heat, then the liquid warms up too. So then the liquid warms up. Now we get to what temperature becomes interesting again for water. Well, obviously 100 degrees Celsius, or 373, let me draw it like this, or 373 degrees Kelvin. I'll do it in Celsius because that's what we're familiar with. What happens? That's the heat, that's the temperature at which water will vaporize, or which water will boil. But something happens. And why is it? They're really getting energy, kinetically active. But just like when you went from solid to liquid, there's a certain amount of energy that you have to contribute to the system, and actually it's a good amount at this point, where the water is turning into vapor, but it's not getting any hotter. So it's turning into vapor, but it's not getting any hotter. So we had to keep adding heat, but notice the temperature didn't go up, and we're going to talk about in a second what was happening then. And then finally, after that point, where we're completely vaporized, or we're completely steam, then we can start getting hot. The steam can then get hotter as we add more and more heat to the system. So the interesting question is, I think it's intuitive that as you add heat here, we're going to get our temperature is going to go up. But the interesting thing is what was going on here. We were adding heat. So over here, we were turning our heat into kinetic energy. Temperature is average kinetic energy. But over here, what was our heat doing? Well, our heat was not adding kinetic energy to the system. The temperature was not increasing, but the ice was going from ice to water. So what was happening at that state is that the kinetic energy, the heat, was being used to essentially break these bonds. And essentially bring the molecules into a higher energy state. So you're saying, Sal, what does that mean, higher energy state? Well, if there wasn't all of this heat and all of this kinetic energy, these molecules want to be very close to each other, right? For example, I want to be close to the surface of the Earth. When you put me in a plane, you have put me in a higher energy state. I have a lot more potential energy. I have the potential to fall towards the Earth. Likewise, when you move these molecules apart and you go from a solid to a liquid, they want to fall towards each other. But because they have so much kinetic energy, they never quite are able to do it. But their energy goes up. Their potential energy is higher because they want to fall towards each other. By falling towards each other, in theory, they could do some work. So what's happening here is when we're contributing heat, and this amount of heat we're contributing, we could either call it, when you're going in, it's called the heat of fusion. Heat of fusion. Because it's the same amount of heat regardless of how much direction we go in. When we go from solid to liquid, it's you can view it as the heat of melting. Right? It's the heat that you need to put in to melt the ice into liquid. When you're going in this direction, it's the heat you have to take out of the 0-degree water to turn it into ice. So it's the heat that you're taking that potential energy and you're bringing the molecules closer and closer to each other. So the way to think about it is, right here, this heat is being converted to kinetic energy. Then when we're at this phase change from solid to liquid, the heat is being used to add potential energy into the system, to pull the molecules apart, to give them more potential energy. If you pull me apart from the Earth, you're giving me potential energy because gravity wants to pull me back to the Earth, and I could do work when I'm falling back to the Earth. A waterfall does work. It can move a turbine. You could have a bunch of falling sows move a turbine as well. And then once you are fully a liquid, then you just become a warmer and warmer liquid. Now the heat is once again being used for kinetic energy. Right? You're making the water molecules move past each other faster and faster and faster to some point where they want to just completely disassociate from each other. They want to not even slide past each other, just completely jump away from each other. And that's right here. This is the heat of vaporization. So this is the heat of vaporization. Heat of vaporization. And that the same idea is happening. Before we were sliding next to each other. Now we're pulling them apart all together. So they could definitely fall closer together. And then once we've added this much heat, now we're just heating up the steam. We're just heating up the gaseous water. And it's just getting hotter and hotter and hotter. But the interesting thing there, and I mean at least the interesting thing to me when I first learned this, is that there are these states that you can have. Whenever I think of 0 degrees water, I always say, oh, it must be ice. But that's not necessarily the case. If you start with water and you make it colder and colder and colder to 0 degrees, you're essentially taking heat out of the water. You can have 0-degree water and it hasn't turned into ice yet. And likewise, you could have 100-degree water that hasn't turned into steam yet. You have to add more energy. You can also have 100-degree steam. You can also have a 0-degree water. Anyway, hopefully that gives you a little bit of intuition of what the different states of matter are. And in the next problem, we'll talk about how much heat exactly it does take to move along this line, and maybe we can solve some problems on how much ice we might need to make our drink cool.